Concrete is the world's most used man-made material, with estimates of 30 billion tons produced globally each year. It builds our homes, hospitals, highways, and government buildings. But the cement used to make concrete is also one of the planet's biggest climate contributors, accounting for roughly 8% of global CO2 emissions.
The process emission is during the process of making the cement. We have to put the raw material, limestone, in the kiln. And then that will break down limestone, which is carbon calcinate, to carbon oxides. And the CO2 will come out as a byproduct. The second part is what we call energy emission, because that calcination process will require extensive energy. For example, the temperature of that kiln has to go up to 2,500 Fahrenheit. 1 ton of the cement production typically leads to 1 ton of the CO2 emission.
Increased pressure from governments, corporations, and public interest groups to reduce the carbon footprint of cement has impacted the demand for low-carbon or carbon-neutral concrete solutions. Contractors, transportation agencies, and other key players are now prioritizing greener materials in procurement.
Building materials and construction make up about 11% of the annual global ECO2 emissions, and of that 11%, 6 to 8% is typically made up by cement. Cement companies and ready-mix companies are starting to look at ways to lower the embodied carbon, either through the use of direct capture technologies or CO2 mineralization technologies, or the introduction of alternative materials into the clinker and production of cement. From a construction standpoint, we're seeing an increased pressure from both owners as well as architects to drastically reduce the GWP requirements for delivered mix designs. We're starting to use more supplementary cementitious materials, different technologies that increase cement efficiencies, and focus on materials that can have a drastic input without impacting performance or production.
As with many industries, labor is in short supply. As a result, the industry is seeing increased inconsistency in concrete mix handling, placing, and finishing. As concrete is being pushed to do more with less, high-performance admixtures are becoming mission-critical.
How do we increase the workability and finishability of our concrete? How can we reduce our clinker and our cement? We use natural pozzolans, but there are some good and there's some bad natural pozzolans. We like to use liquid fly ash. It's an admixture, and what this admixture does is it increases the density and flexural strength of our concrete. Flexural concrete is very helpful for us on bridges and airport jobs or highways. We can reduce the cement, increase the density and flexibility of our concrete. Less clinker, less cement means less travel time, less trucks on the road, more durability, and better finishability.
Now, developments in nanotechnology are enabling admixtures that help de-risk variability in project execution, improve finishability, and compensate for inconsistent craftsmanship.
E5 is developing NanoSilica for the betterment of the concrete finishers. Nanotechnology is the answer to a lot of the problems that we've had within the concrete finishing industry.
We use these admixtures to have better quality, and workability and finishability means everything at the end of the day for our finishers. If the owners are satisfied and the men that work with our product every day love to work with it, we can go home at the end of the day knowing that we gave them the best product that we could possibly give them. That's what makes us sleep better at night.
Advanced performance and durability through smart materials enables sustainable concrete that optimizes mix designs and improves quality control, all while supporting labor efficiency and job site productivity.
NanoSilica has helped optimize the mix design to be more effective. These nanoparticles are able to cause a dissolution effect with the cement particle to get more cement dissolution, or what we would call dissolving the particle to achieve a more cement paste, more cement hydration. It improves durability in the concrete by internally curing. Internal curing is the holy grail of concrete. You've got to find the right particle size, you have to have the right surface area, and you have to have the right modifications that allow colloidal silica to create the internal curing within the concrete matrix. Not all colloidal silicas can produce this type of reaction within the concrete.
In addition, the nanotechnology eliminates the need to use scarce water resources, various chemicals, and other materials used in connection with traditional concrete mixes.
E5 NanoSilica can help us conserve our natural resources. With internal curing, we now can eliminate burlap and visqueen and water on top of any concrete application. And by eliminating those type of traditional curings, the schedules are met, labor goes down, and trash being sent to the landfills has been significantly reduced by this simplification?
So the overall environmental benefits are twofold. The ability to produce a concrete that has a lower permeability and has a higher level of durability and is capable of lasting for longer in place using the same or less materials. Internal curing inside of the concrete itself is what makes the concrete stronger and allows more of the cement particles to hydrate over a longer period of time. The second portion of it is the ability to reduce the actual GWP of the concrete mix designs. And we're seeing between 10 and 15% ability for cement reductions across the U.S. That ability to reduce cement in a mix design is key for designing a sustainable or lower carbon footprint concrete.
Unlocking a future where durability and sustainability go hand in hand. NanoSilica enables a built world where every structure leaves a lighter CO2 footprint on the planet.